Check out the second example for the deck design. Welcome to Bridge Engineering. This video is dedicated to the graduating class of 2026. The problem involves an 18-meter-long RC bridge. It has a deck thickness of 200 millimeters, and girder spacing is 2.5 meters. The specified concrete grade is 28 megapascal, and the steel grade is 415. The computed ultimate moment is 72 kilonewton meter per meter, and shear is 95 kilonewtons. Then the service moment is computed as 45 kilonewton meter per meter with shear of 80 kilonewtons. We are to design the deck using a AASHTO strip method. We begin with the main reinforcement, which is the transverse bars. It would be for top and bottom, but we work on the bottom first. For the main rebars, we compare moments, the ultimate versus the nominal. Let's determine the effective depth by taking out the clear cover and bar radius from the deck thickness. The clear cover at the bridge soffit is 25 millimeters, so by using 20 mm diameter rebars, the effective depth is computed as 200 less 25 minus half of 20 mm, which is 165 millimeters. Instead of iteration of the two equations, we plug A into the moment equation, thereby having a quadratic formula. This may be a longer formula, but it's a complete plugging in operation, where we place 28 for FC prime, B is 1000 millimeters, effective depth is 165, Fy is 415 megapascal, and ultimate moment is 72 kilonewton meter per meter. The required steel area for the bottom reinforcement is 1251.004 square millimeters per meter. Since we are using diameter 20 mm RSB, we compute for the number as the steel area divided by the cross-sectional area of an individual bar. That's 1251.004 upon pi over 4 of 20 squared, giving 3.982 pieces. Now for the spacing. Take a strip of 1000 millimeters and divide this by 3.982, which gives 251.126, rounded to 250 millimeters. Now compute for the main rebars on top. When using a software, we can identify the positive and negative moments, and the top reinforcement should use the negative moment. Since we haven't got any input for the negative moment, we still use 72 kilonewton meter per meter. Just like what we did earlier, we take the effective depth from 200 less the concrete cover of 50 millimeters, then the radius of the bar, which gives 140 mm. Now place this with the other parameters into the long equation for the steel area, where again, F'C is 28, B is 1000, D is now 140 mm, and Fy is 415. And we still use the ultimate moment of 72 kilonewton meter per meter. The result comes out as 1521.007 square millimeters per meter. We then determine the number of bars by dividing this figure with the cross-sectional area of the specified bar. That is 1521.007 upon pi over 4 of the square of 20, and we get 4.842 pieces. And for the spacing, we have the width of 1000 millimeters divided by 4.842, which gives 206.547. Taken as 200 millimeters. With the main reinforcement already taken care of, we compute for the longitudinal reinforcement, starting with the bottom bars. This is determined by taking 2/3 of the bottom main reinforcement, which we had computed as 1,251.004. So the longitudinal steel area is 2/3, giving 838.1725 square millimeters per meter. The longitudinal bars are smaller than the main bars, so we use 12 mm RSB. The number is then computed from the area of 838.1725 divided by pi over 4 of 12 squared, giving 7.411 bars. The spacing comes from 1000 over 7.411, resulting to 134.933, and we take it as 125 millimeters. The longitudinal bars at the top is for temperature and shrinkage. This is computed as 3/4 of the gross concrete area divided by the steel's yield strength. We use 0.75 of the concrete strip of 1000 millimeters with a deck thickness of 200 divided by 415, which gives 361 square millimeters per meter. With diameter 12 rebars, we divide the area by pi over 4 of 12 squared, and that gives 3.19 bars. The spacing is then 1000 over 3.19, and that is 313.48 mm, taken as 300 millimeters. The top and bottom longitudinal bars are placed within the main reinforcements. Let's illustrate what we just computed. If we take a 1 meter strip of the bridge, where the span is the bridge width, according to the AASHTO table, the concrete cover on top is 50 millimeters, and at the bottom is half of that. The top main rebar is 20 mm diameter, which are spaced at 200 millimeters on centers, and the bottom are also D20 RSB spaced farther at 250 millimeters. For the longitudinal bars, we place diameter 12 mm rebars is spaced at 300 millimeters on top, and the same diameter but spaced closer at 125 millimeters at the bottom. After designing the reinforcement, we verify the limit states. For crack control, we use the spacing, where the maximum is through 123,000 of gamma E over beta S by FSS, less twice of D sub C. We start with FSS, which is the service moment over the area by J and D. We know the service moment is 45 kilonewton meter per meter. And for the bottom bars, the steel area is 1,251.004, with the effective depth as 165 mm. We then need to compute for J, and that is computed with K, or the lever arm. The steel ratio raw is the steel area over the concrete area. That's 1,251.004 over 1 meter of 165 mm, which turns out as 0.007582. Then the modular ratio N comes from E of steel over E of concrete. The modulus of elasticity of steel is constant at 200,000, but E for concrete is 4,700 by the root of F prime C, or 4,700 times the root of 28, which gives 24,870 megapascal. N is then 200,000 over 24,870, or that is 8.04, rounded as 8. We can then compute for K, which is just combining raw and N. So plug in raw of 0.007582 and N of 8. Then K is 0.293. The lever arm J is then 1 less a third of K. That's 1 less 0.293 over 3, which turns out as 0.902. Now we can solve for FSS as 45 million Newton millimeters over 1251.004 by 0.902 times 165, which makes 241.593 megapascal. Next is beta S, where we have the total deck thickness of 200 millimeters. We compute for DC as the cover plus the bar radius. DC is 25 plus half of 20, which turns as 35 millimeters. Beta S is computed as 1 plus 35 over 0.7 of 200 less 35, and that gives 1.303. With normal conditions, gamma E is 1. So the maximum spacing is 123,000 of 1 divided by 1.303 by 241.593 less twice of 35. The spacing is 320.721 mm. For the check, compare the actual spacing with the maximum spacing. The actual was 250, which is less than 320.721 mm. So the bottom RSB spacing is okay. Do the same check with the top bars. We compute for FSS again, using the same service moment of 45 kN per meter. The steel area for top bars is 1,521.007 square mm, and D is 140 millimeters. Again, we are to solve for K and take the reinforcement ratio, which is 1,521.007 over 1,000 by 140, where ρ comes out as 0.010864. The modular ratio of 8 doesn't change. K is then with ρ of 0.01086 and N stays as 8. K is simplified as 0.339. So J is 1 less 0.339 over 3, which results to 0.887. Completing all the parameters, we take FSS as 45 million Newton millimeters over the area of 1,521.007 with J of 0.887 and D of 140. FSS comes out as 238.246 megapascal. For beta S, use the total deck thickness of 200, and for top bars, DC is computed as 50 plus half of 20, and that is 60 millimeters. Beta S is then 1 plus 60 upon 0.7 of 200 less 60, giving 1.612. Using gamma E as 1, the maximum spacing is then 123,000 by 1 over 1.612 by 238.246 less twice of 60, and this gives 200.22 millimeters. Compare this with the actual spacing of 200 mm, which is just the maximum spacing. This validates that the bottom reinforcement is okay. The other check is for shear. This check is to validate the nominal shear and the actual concrete strength. We start with the bottom bars. The concrete strength is 0.166 times the root of 28 times the width of 1 meter and the effective depth of 165 mm. This results to 144.9 kilonewtons. The nominal shear is then taken as 0.9 of V sub C, which is 130.44 kilonewtons. The ultimate shear of 90 kilonewtons is way smaller than the nominal shear, which means the slab thickness is okay. Although the comparison is with the concrete strength, let's take the top bars as they have a smaller effective depth. V sub c 0.166 with root of 28 times 1 meter and 140 millimeters effective depth. V sub c is computed as 123 kilonewtons. So the nominal shear is 90%, which makes 110.7 kilonewtons. The ultimate shear of 95 is still lower than 110.7, so the slab thickness passes.